Welcome to the 12th video in Introduction to Quantum Field Theory. We will cover the first part on Noether's theorem, so we'll talk about spacetime symmetries. There are other things that we will cover, and that will be in the next video. So Noether's theorem is that for any continuous symmetry within a physical system, there exists a corresponding conserved quantity. So an example of this in the set of spacetime symmetries is rotational invariance, where you can rotate a system, and if I say rotate everything in space by 90 degrees, then it doesn't matter. The physics will still be the same. Or, if I were to rotate this iPad that I'm drawing on right now, if I rotate my iPad, well, it's still an iPad, it still works, everything's the same. This means that there's conservation of angular momentum. Similarly, if there is spatial translation invariance, that is, if I move it in space and the physics are the same, then there's conservation of momentum. And if I move it through time, or, we don't perceive time as an extra dimension, but it just existing, and the fact that, so if something works the same way yesterday as it does today, then there's conservation of energy. A lot of something interesting. This is just kind of an aside. A lot of things, or a lot of physicists say that Noether's theorem is kind of like the most kind of like beautiful or obvious, or not obvious, but like a strange thing that they didn't expect to see in physics. I actually didn't really feel that way about space-time symmetries. I feel like rotational, spatial, and temporal invariances leading to conservation of these things is kind of obvious, but what I thought was super cool, and which the next video will cover, are internal symmetries, such as shifting the field, shifting the local coordinates of fields. And if there's invariance to the physics, then there's conservation of something called conjugate momentum. And if you introduce phase shifts to systems and they are invariant, then you get something called conservation of charge. And these are the things that I think know this theorem shows to be really cool. And so this video will present space-time symmetries and just introduce the way in which Noether's theorem is used. So to use Noether's theorem, three things are needed. The first is that a physical transformation needs to be chosen. So that is, you map from some position to some different type of position in some way. And two, second thing you need to do, or this transformation needs to be plugged in to the Lagrangian density. Lagrangian density. So what this means exactly is that the Lagrangian density of a field gets mapped to the new Lagrangian, which has some changed field, some changed Here, I'll write it like this. And then third, the new Euler-Lagrange equation needs to be derived in order to see what new condition extremizes. Oh, that's wrong. Extremizes the action, which in this case, this little thing is going to be so equal to 0 if and only if the change in the Lagrangian density is equal to 0. So this new condition that you find in step 3 that extremizes the action, this new condition will be a continuity equation dictating the conservation of some physical quantity. So let's take a look at translational invariance. So space-time. Translational invariance. Well, this corresponds to taking a vector x and mapping it to itself plus some other vector. So it's being translated. Well, this implies that the field also changes. It maps to the field or to, what do you call it? F prime x mu plus a mu, which is just equal to f of what the field value at x mu is minus how much the field changes in that direction. So minus how much the field changes in that direction. And then the amount it actually changes by, which is this. You might be wondering why there's a minus sign here instead of a plus. Well, this tells you how much the field changes. And so if you're looking at the field value if you're looking at the field value at some other point, then you're, okay, let me put it this way. If I have a field or I have space-time, so this is space-time. Say I'm looking at a point here, and then there's a point here. This is x, and this is x plus a. Then if the field should kind of be the same, so the field is going to be above it. So just imagine the field's above it. So if I'm looking at the field here, and I want to see hang on, how much the field change or is here, and then there's the field value here. Well, then if I start looking here, then I'm going to need to know how much the field changes between them. So this vector A. So there's a derivative that will tell you how the field changes along the path, and then A will tell you how long the path is. So that's what this is. Okay, so then this implies that the change in the Lagrangian, which is it's going to be, well, phi prime here is just phi minus this, and then minus flip. And then minus the original Lagrangian. So it's just phi, phi, and then x mu. Well, we're going to we're going to skip a little bit forward using all steps from the last video. So we're going to skip to the end because the math is exactly the same as what uh, happened up here. The math is exactly the same. So we skip these steps and we end up with a negative derivative or gradient of this quantity times d mu, or actually no, d nu phi a nu plus change in the Lagrangian. I'll just write it like this. Change in the Lagrangian is equal to negative change in the Lagrangian again. So just there are going to be lots of steps to simplifying this expression. Okay, I don't know why I started writing the same one twice. Bad. But let's see. So using the steps from the last video, we get this value. And then the next thing we want to do is we're going to try to put this term into here. So we want to eventually pull out uh, a minus sign. We want to pull out a minus sign and a partial mu from here. So the next thing we're going to do is bring this down and this up. So we can copy and paste. So we swap that. And we're also going to swap these indices as well. So now you can see that these indices are the same. Well, then we're going to just do some relabeling. We're just going to call this new and this new as well, because this and this, or because this is independent from this, you can relabel them. And then you can take this and we can finally pull out an a mu or a nu and pull this out to the right. The next thing we want to do is pull out, oh, hang on. No, this is not correct. What I just put. Bad, bad, my part. Bad, 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 bad. Okay, yes. So the next thing is that we want because we can pull out a new on both of these, but we cannot again. So wasn't completely wrong. I just needed to what do you call it? Put this here and then put an extra bracket like this. Yes. So we've combined them into a smaller thing, but now we want to add that or combine these two terms. So there is an old thing we talked about, and that is the fact that there's this relationship right here. The Kronecker delta will combine with one index and replace, or it'll annihilate this index, but then leave this new here. So you end up swapping indices. So that's what you end up doing. You get negative, or yes, just copy. I'm just going to copy this if I can off my game. I'm off my game. Well, I can put mu new and then mu right there, which means I can now pull out a d mu, a partial mu. So I can pull out a negative partial mu from this equation to get a partial mu of this, then minus, because we pulled out a negative, so there ends up being a minus sign, minus the Kronecker delta of the Lagrangian, a nu. So if this is an invariance, meaning that this doesn't change the system, and we know that it doesn't change the system, then we can say, or so if this is an invariance, then we know that this is going to be equal to 0. So what's the condition that makes this equal to 0? Well, turns out to just be setting this value, or this right here, equal to 0. So if this is equal to 0, you can actually just divide out this term, because there will be a 0 here, so you can just divide this out. The same with the negative sign. So you end up with this equation, or no, you end up with this equation right here being equal to 0. And this is this is typically written T mu nu, and it is the energy momentum tensor. Therefore, we have shown that the gradient of this tensor is equal to 0. We've shown this condition. So there is a corresponding quantity that does not change. It is invariant. So what do these components actually represent? You have the conservation of energy, so T naught naught. This actually is energy, and T naught J, this is momentum. So you have the conservation of energy and momentum, hence the term energy momentum tensor. So this is one example of how to use Noether's theorem to actually derive the conserved quantity from a symmetry of a system. In the next video, we will cover this for internal symmetries.